So, if you're anything like me, the first time you seen this formula, you probably weren't too pleased either. So, in the next 5 minutes, I'll make sure that you not only fully understand it, but that you can answer any question that you may be faced with in the exam. Right, let's get started. It were about 350 years ago that a French fellow named Lagrange first came up with the notation that we use today. Thank you, Lagrange. Whilst it can look confusing at first, it's actually not as complex as it looks. So let's start to unpack it. We can see that the function's input is x, and its output is f dash of x. This just means the derivative of f of x. There's actually about four sort of common ways to denote the derivative, just made by different guys. I just thought, yeah, we'll keep going. More. The last one wasn't good enough. So don't get confused. They pretty much all mean the same thing. Right, okay, that's enough about notation. Let's have a look at the meat of the formula. So we know that if you want to find the gradient of a straight line, we just whack 2 points on the line. It doesn't really matter where. And we can use this formula, the change in y over the change in x, to find the gradient. Well, we can roughly do the same for this curve by simply putting 2 points on the curve and using the formula to find the gradient between those 2 points. So let's put point 1 here and point 2 a little further along the x-axis. We won't be too specific for now, as it doesn't really matter where these points are. So let's just say point 1 is at x, and point 2 is at x plus h. So the y-axis values, or the outputs, are f of x and f of x plus h. We'll join these 2 points with a green line. Perfect. So we have our 2 points. Let's plug them into the formula so we can get the gradient of the green line. Doing this, we get f of x plus h minus f of x all over x plus h minus x. Well, since x minus x cancels, we get f of x plus h minus f of x all over h. Looks familiar, right? However, you'll notice that this doesn't really give us a very accurate answer. In fact, the further away these 2 points are, the worse the approximation to the true gradient in black actually is. So instead, let's bring these 2 points closer to get a more accurate approximation. We can do this by making the h value smaller. You'll notice that as the h value gets smaller, the rough approximation gradient in green gets closer to the true gradient in black. This is where the limit comes in. This section simply tells us that we're going to make h really small so that we can simply ignore it. Now we understand the formula. Let's put it to work. Let's find the derivative of, say, x squared using the method of first principles. So since we're looking for the derivative of x squared, we'll set f of x equal to x squared. So what about f of x plus h? Well, it's simple. Wherever we see an x, just replace it with x plus h, since x plus h is the input of f of x plus h, in the same way that x is the input for f of x. So with this logic, we know that f of x plus h is going to be x plus h squared. Also, key point here, please use brackets. I can't tell you the amount of times I've done it. I've tried to not use brackets to speed things up, and it just does not work in the end. So always use brackets. So altogether, we get x plus h squared minus x squared all over h. Expanding and simplifying this gives us 2x plus h. Now, this is where we use the limits. So as h tends to 0, i.e. it gets really, really small, we can consider it to be so small that we can simply ignore it, making our final answer 2x. Now, the real beauty of these questions is that you can easily check your answer by simply differentiating using the times and take rule. I'll link below a video where I covered this method. Yeah, right, well, if you like that, let me know, and I'll perhaps make some more on a different topic.